Hello everyone. So we have been seeing a series of advanced passive strategies, and today we will have a look at another advanced passive strategies, which is the Sunspace. Now Sunspace is a very popular passive solar technique, and this is used to collect energy from the sun. A sun space is normally south facing. It is a glazed area which is located mostly outside of the main fabric envelope of the building. This space naturally heats and cools, allowing daytime temperature to rise more and nighttime temperatures to fall further than the comfort zone temperature of the adjoining living space. So, this enables the indoor to maintain a temperature which feels comfortable through day and night. Now, climatic conditions in which sun spaces are used are primarily cold climate and temperate climate. In the cold climate, the temperature could drop down to 6.7 and further down even to 1 degree centigrade. In the temperate climate also, the temperature could fall somewhere between 7.2 degrees to 10 degrees. So, attached sun spaces, also called as conservatories, they work much like a vented trombe wall. They can heat spaces both through radiation as well as convection. The difference is that the space between the glass and the thermal mass creates a habitable space. So, in other kind of heating spaces, the place where the heating actually happens is usually not habitable, but in sun spaces, these become habitable or usable space. So, the main principle of south facing sun spaces and conservatories is similar to a trombe wall, but with a large and therefore functional cavity. This cavity becomes functional because the space is large. Glass allows solar radiation to fall onto this space. So, the solar beam penetrates through the external glazing here, provided here, and it traps and keeps the heat inside. Part of the heat is stored in the thermal storage medium, which is the wall and the floor. This will be redistributed back to the space at a later date, which is at night. And part of the heat can be directly carried into the space through convection, and the convection currents starts. So, the air convection through the vent opening at the wall when heating is needed immediately can be opened and it start the convection process. At night, what happens? At night, the night sky acts like a cooling sink and heat starts to get radiated outside because the indoor is warm and outside is cool. Heat from the storage medium, which is the wall and the floor, also radiates out, causing a convection current inside. Of course, there is radiation of heat between the inside and the outside through the walls too. Now, a uncomplicated approach for absorbing solar energy in the building is the use of greenhouse effect and greenhouse optimization. In the greenhouse, when I say greenhouse, I don't mean greenhouse gases, I mean the actual conservatory greenhouse. It traps the radiation from the sun without any other element, with only a translucent or a transparent medium, and it makes it a very important system in cold climate. For utilizing the sun's energy as passive heating, it becomes very important for us to store the energy, distribute the energy, and conserve the heat. And in that scenario, the sun space becomes very important. So, it's a very interesting architectural find in the energy attitude of solar radiation usage, which gives energy benefits in terms of bringing down the demand for winter energy. Sun spaces are designed to collect solar energy. So, the energy is collected how? In floors and the walls. So, the collection happens through the glass and stored in the floor and the wall. So, the solar energy is how much of solar energy is collected depends on the quality of the system and also the weather conditions. So, glass allows the solar radiation to penetrate through the glazing and it keeps the heat inside. A small part of the heat is stored in the thermal storage, which is nothing but the wall and the floor, and this gets redistributed back to the space at night. So, sun spaces are primarily designed to collect the sun's energy and reduce the dependence on other forms of energy. So, the solar radiation gets transmitted through the glazed shell, and this is absorbed by the opaque and glazed walls, and some of it is absorbed by the surrounding environment of the sun space. Eventually, this energy, which is in the form of heat, is again transmitted to reach into the adjacent spaces. Sun spaces are usually used for buildings for heating in winter and cold seasons, taking into account reducing the load on the energy system to increase the heating. In the process of the sun space designing as a passive technology in buildings, its application in summer season is not really considered, seeing that overheating defect in the hot time happens, and consequently the advantage of this passive system is not really utilized during the summer time. In general, the operation of the solar sun space is with the help of solar energy, the glazing, which is actually the collector, solar energy is the source, glazing is the collector, heat storage, which is in the form of floor and walls, is the storage system, and then the dispersion happens by means of natural phenomena like conduction and convection. It allows for heat conservation and gives us some scope for controlling the way heat must flow back to the indoors. Now, let us look at the operation of the sun space. The solar energy first is the direct source of energy and gives us direct radiation. The total direct solar radiation available for a sun space is related to the location of the sun space, the prevailing climate conditions of the area, and the orientation of the window area. If we look at the effect of glazing, the glazing is responsible for solar gain as well as heat losses. Transmittance, the radiation that is neither reflected or absorbed is transmitted. Translucent materials create diffusion, which means radiation that enters the sun space gets scattered and distributed evenly in the entire sun space, avoiding areas of overheating. Then absorption. So, two main parameters that can affect the reflectance and absorption is the material and the angle of incidence. Then multiple glazing. The use of more than one layer helps in reducing heat losses as the gap between layers act like an insulation. So, having two layers of glass with a gap in between prevents heat loss. However, since the transmittance is connected to the absorptance and the reflectance of the glazing, by increasing the glazing layers, the transmittance also gets lower. Thus, even if the heat loss reduces, at the same time, heat gain also gets adversely affected. And then the last is orientation. In order to achieve optimization in design, the glazing has to be perpendicular to the radiation received at any time, but that is not always possible. So, if we look at the factors that affect the functioning of sun space, first is solar energy, the intensity of solar energy that is got. Second is the transmittance of glazing. So, first is solar energy, its intensity. Second is the transmittance of the glass. Third is whether it is translucent or transparent. Fourth is its reflection and absorption properties. Fifth is the use of multiple glazing. And sixth is the orientation of the glass with respect to solar radiation. So, these are the parameters which affect the solar radiation that can be tapped and captured. Then the next parameters is the heat storage. So, the first phase of heat storage procedure is the solar radiation absorption. The surface color and the texture are the two main parameters that affect the absorptance. Dark colored surfaces in general absorbs higher portion of solar radiation than light colored. Second is heat storage mediums. The effectiveness of heat storage is higher when the direct solar radiation strikes a surface. So, the sun space floor or the common wall with the adjoining room are the preferable locations for heat storage to happen. Third is the heat capacity of materials. Now, heat capacity is a physical property of the masonry, and it is defined by the amount of heat needed in order for a mass to change its temperature by 1 unit. Fourth is the thermal conductivity. Again, that is a physical property of the material. In order to enable the heat to get stored in the material, it needs to be transferred from the outside surface through its body. And this heat flow is always from hotter to colder body. Fifth is the masonry. The masonry used at a sun space for heat storage needs to have high heat capacity as well as thermal conductivity. So, good materials which have both high heat capacity and thermal conductivity are normally considered to be brick, concrete, stone. So, we have already seen thermal mass as a concept, and that is what you need to understand, that the thermal mass must be high of the flooring material as well as the walling material. The heat capacity of water is higher than the materials used in masonry. So, they can absorb and utilize higher amounts of solar heat. And this is the concept which is also used in the water wall. I am just trying to connect both of them. Then next is heat conservation. Now, the most common are heat losses through the glazing, the infiltration, the exfiltration, and the conduction heat losses through its opaque surfaces like the floor, the wall, and the ceiling. So, first is convection losses. So, convection heat losses occur mainly due to the contact of warm air that flows in the sun space with the cool interior surface of the glazing. Then radiation heat loss also happens. So, radiation heat losses, especially through the glazing, are a significant contributor to the general sun space heat losses. Third is losses through glazing. So, the most common measure to increase heat flow resistance through the glazing is the use of double glazing that are separated by a thin layer of air, and this air functions as a insulation. Fourth is opaque surfaces insulation. Now, it is preferable to use no insulative layers in common walls so that the heat flow to the interior is not impeded. The addition of insulation to the other opaque walls of the sun space, such as wall, ceiling, and floor, can help to reduce the conduction heat losses. Fifth is movable insulation. The insulation can be placed on glass during the night time, outside or inside the sun space glazing, in order to prevent the heat flow to the exterior and therefore capitalizing on the higher amount of heat storage produced during the daytime. So, if there is some insulation provided only at night, then this heat loss can be reduced. So far we have seen what should be the properties of the glazing, we have seen what should be the properties of the wall, and here we are seeing the factors that are responsible for the transmittance of heat. Next we will see heat distribution. So, the role of thermal mass in sun space is to store the heat that is distributed to various rooms during diurnal periods without sunlight or during the night. The materials that are used, they must have a thermal mass that needs to have very high volumetric heat capacity. Normally we saw that materials for heat storage should be something like concrete, brick, water, etc. Compressed earth blocks also function very well. So, this moving elements within the sun space or other rooms such as water tanks can also serve as good thermal mass, because you can remove the thermal mass and put it in some other space where heating up is required. We will look at heat distribution. So, passive solar sun space are indirect systems since the heat is produced in the sun space and then has to be delivered to the adjoining room through a medium. Sun space integration. The way the heat flows between the spaces is directly dependent to the integration level of the sun space to the adjacent spaces. Sometimes we can have a lean-to space, that is, it can shade adjoining areas of the facade and can reduce natural light into adjoining spaces. Or the second type is embedded spaces. The sun space does not restrict daylight to adjoining windows or does not cause any other inconvenience, but it can become self-shading. So, heat transfer through conduction among common walls and air circulation through openings can happen. In a sun space. So, sun space is a very simple and uncomplicated approach that can be adopted to tap the solar energy in a building. The greenhouse effect traps the solar energy without the use of any other element except for the transparent component that makes it a key system in cold climates. For utilizing the solar energy as a passive heating system, it is important to consider storage, distribution and conservation of the heat such as the sun spaces. So, sun spaces are very interesting solutions in energy attitude of solar radiation utilization because they give a lot of energy benefits in terms of reducing the demand for keeping the building warm in winter. These are also designed to collect solar energy to reduce the need for any other auxiliary energy system. The solar energy which is obtained depends on the location of the place to understand the intensity of solar radiation. Some of the solar radiation which is transmitted through the glass can get absorbed by the opaque walls and also through the floors. It can get absorbed to the floors and eventually heat energy gets transmitted to the adjacent spaces. These are generally used for buildings for heating in winter and cold climates, considering the reduction in the building's heating load, and in the process the sun space becomes a passive technology of buildings. Its application in summer season is not considered because one needs to understand how to utilize the space during summer when the building does not need to get heated. But the advantage of sun space over any other space is that the sun space is a habitable space. Thermal storage materials in the sun space collect this heat during the day and this heat is distributed to adjacent space. But its usage in summer becomes questionable. And therefore, what can be done is, in summers, the sun space can be impeded from direct solar beam by using shading devices and ventilation by opening some part of the glazing of sun space as much as possible. Operable vents are often designed at the top of the sun spaces where temperature is highest and at the bottom where temperature is lowest. So, these vents can circulate air between sun space and indoors or directly exhaust hot air to outsides. They can be operated mutually or with thermostatically controlled motors like mechanical fans. And this can be used to increase the air circulation to the entire house where natural convection is not adequate. So, a passive solar system with a sun space which comprises of a glazed portion of the structure is adjacent to a living room. Sun spaces can function as an intermediate space between the inside and the outside, and they can act like a buffer space. A further effect of the sun space is to shelter the envelope from wind chill and rain. This can also be used to start natural ventilation. Warm air can flow into adjoining spaces through openable vents located in the common wall at the top of the sun space. Cool air is returned from the living spaces through lower vents to be heated as part of a convective loop. The other function is mechanical ventilation can extend the penetration of preheated ventilation into areas of the house that are not adjacent to the sun space. Heat is collected from the upper part of the sun space and blown through ducting to other areas of the house where the sun space is not directly accessible. So, they are these areas. Sometimes indirect gain can also happen. Heat is transferred to the living room through a masonry common wall. The position of sun space in relation to the entire building can vary, and some positioning and shape options are shown here. In figure 1, you can see that the sun space is it is added, it is an attached kind of a sun space as shown in this picture. So, this is attached. Whereas, in option 2, it is a embedded one as can be seen in this picture. Option 3 is a combination of attached and embedded. So, this is partly embedded as can be seen in this picture. M4 shows that the sun space becomes part of the house, or it connects two parts of the house. So, it becomes like a one element of the house. The fifth option shows the sun space to be more like a courtyard space, and the sixth option is that the sun space encloses the building. So, this is enclosed as shown in this figure. So, these are the ways in which the sun space can be located in a building. Let us now look at the limitations of a sun space. So, first is the sun spaces are easily overheated in summer, and this problem can be resolved by number 1, shading from the sun. So, external solar shading from a roof overhang or adjacent louvers can help this. Then second is deciduous trees, though the leafless trees to an extent continue to shade. Second is ventilating the sun space by placing operable vents to the exterior through the roof of the sun space. These can be automatically opened and should be coupled with vents at low level to enhance the stack effect. Third is air permeability and air tightness. Air tightness around windows and doors should be particularly effective to reduce heat loss to the sun space when the space cools to temperature below the adjoining living area. And fourth is controls of ventilation. If automatic vent operation is not provided, the building user needs to be fully aware of the need to control the vents properly. Where automatic controls are provided, users should be able to set them to the desired level of comfort. Thermal mass within the sun space is another criteria. So, the inclusion of thermal mass results from the clear design decisions, where the sun space acts primarily as a buffer space. The thermal mass extends the period of heating within the sun space, where the sun space acts primarily as a passive solar collector, and where there is a need for a rapid convective transfer to the living spaces, air and not the mass needs to be heated quickly. This process can be encouraged by use of light and reflective materials. Let us look at the design and construction and the considerations. So, first is an opaque roof. An opaque roof is needed as it provides insulation, it provides shading, and it restricts daylight to the living areas. Then there is need for glazed roof. When there is glazed roof, it optimizes solar gain, it increases heat loss in overcast conditions and at night. It is prone to overheating and is susceptible to leaking. It is also prone to glare. Now, if vents are placed at the top of the glazing, then air from the room will be pulled away by convection in the air gap between glazing and mass wall. This form of passive ventilation is also called as the solar chimney. Let us now look at the types. So, sun spaces types are according to the type of partition between the sun space and the adjacent room. So, a sun space with a thermal storage wall and a direct system. So, this is a direct system cum storage wall. The second one is a sun space with a transparent partition. So, everything becomes like direct transmittance. Third is sun space with thick thermal storage. And the next one is sun space with a trombe wall. So, all these variations are possible. So, basic sun space types according to thermal mass position. First is the thermal mass in the sun space floor. Second option is thermal mass in the thick wall between the sun space and the living area. Third is thermal mass in the sun space and living area floors. And fourth is thermal mass in the sun space of the living walls as well as floors. So, these are the four types of thermal mass position. Let us now look at case studies. Here we look at a case study which is a research paper. Now, the main objective of this study is to apply a combination of solar chimney and sun space to create better thermal conditions in winter and summer for internal spaces. The primary weakness of the sun space is its ineffectiveness during the summer season, and the main issue is the solar chimney in the building, which has the low usage in cold season of the year. So, this study looks at integrating two passive strategies, that is solar chimney and sun spaces in a building, but we will focus primarily on the impact of sun space in this building. So, what was done was a study using simulation as well as field study data collection was done, and then further simulations were done using variations of the sun space. So, A is the base case to which sun space of 4 meter square was attached, and the third option was a combination of sun space and solar chimney was attached. So, the first type only is for 15 meter square comprising of the base case. So, the study showed that the temperature and humidity output resulted from the software on an hourly basis throughout the week in July 2016, and it compared with the experimental results and were found to be fairly in agreement. It was found that the variation among type A and B is approximately 2 degrees centigrade. Though the utilization of solar chimney in sun space was there, the room temperature rise due to improvement in building heating process through the roof. The mean temperature variation between type B and type C is about 1 degree centigrade, but it is not much of a concern to us here because we are not studying the impact of solar chimney. So, this variation between type A and type B is of concern to us in this lecture, and the outcomes indicate that the sun space system decreases the indoor temperature by 2 degrees centigrade in hot season and increases it by 3 degrees centigrade in cold months. And if you look at the annual cooling and annual heating load, there is a difference in the annual cooling and annual heating load as well as annual energy consumption when sun spaces are used as compared to the base case. So, sun spaces are a system, a passive system which is often used in residential building because they can conserve energy. They give us spaces which can be utilized. They cannot provide the best of indoor conditions, but they have a significant contribution to conserve the energy generating products used for heating and cooling. Further research needs to be done on sun spaces in terms of the position in relation to sun, the size of the glazed surface, the type of glazing, the thermal mass sizes and use of varying materials. So, in today's class, we saw sun spaces comprehensively as a advanced passive technique. We will continue this class with yet another advanced passive techniques next class. Until then, thank you.